SwayamPrabha. Digital India. Educated India.
Yeah, see, somebody, please ask me also. Don't start a small circular conversation. Everybody would like to be involved. But let me tell something in connection with what he was asking. See, I'm saying that, for example, of course, what he is asking is, if you can't prove something, what do you do? It's like helpless. And then how do you keep going like that? But is there some point that we stop? So the point is that sometimes you use a model, and if the model explains everything, you are happy. So for example, in physics, there is a standard model about subatomic particles that kind of explains everything, but then there are problems. It's at loggerheads with quantum properties and with some other non-quantum kind of properties, okay, and there are properties about black holes and deep properties about subatomic particles which is not able to explain. So the point is that you can make some assumptions and get a theory which explains to some degree of accuracy. Up to that point it's okay, but then after that, you don't see. For example, what happens at a black hole? We don't have any math. There's no math, there's no physics, there's nothing available there. It's completely blind. You're blind. People are testing all kinds of theories. Even that is at the cosmic level. At the subatomic level, even inside a proton, okay, how the structure is there inside, that itself is still a mystery. People don't know, and there are questions. People have done experiments, they have made observations which cannot be explained by the standard model. So you see, you're right. The point is that at least in things like this, you can assume something, and then you go in so far as you're able to explain some things using that, you're happy with it. But then where it fails, then you are again at the frontier. You have to search for something else, you see. So it's like that. But the point is that at every place, the hard part is that you have some axioms, and then you build on the axioms, and then you get things. So for example, in math, people have proved, you assume what is called as generalized Riemann hypothesis. From that you can deduce twin prime conjecture. You can deduce Goldbach conjecture. If you have proved, if you assume the truth of the Riemann hypothesis, which is it's a clay problem, it's a millennium problem, okay. So yeah, I mean, you can assume something and show that it has some consequences, but that itself is still an assumption. Until you prove it, it's not true, you see. So that kind of things are, I mean, people can think like that, okay. So Fermat's last theorem was proved by Andrew Wiles and Taylor, and it was it was a corollary to what is called as Taniyama-Shimura conjecture, okay, that every elliptic curve is modular. So the point is that it is, you can find some other statement from which you can deduce this and prove that statement, okay. What people try to do is that they assume something is, you have to prove something is true, you assume it's true and prove something else, you deduce it, and if you prove this something else is false, that means the original thing is also false. People tried, it didn't work. Whatever they assumed as true and whatever deductions they found, those deductions they could independently prove. Not a single case they could find it false, okay. So this is a standard way of, you want to show A is true, from A you deduce B, and find a B says that B is false, then A must be false. But unfortunately, thousands of B's that they deduced from A, all the B's are true, not a single B is false. So this A is still kind of clear, okay. So these kind of things happen, okay. It happens in math. But the point is, math, when mathematicians give a formula, it's like absolute, it's accurate. I mean, otherwise you don't give it. You wouldn't even call it a formula, okay.
Sir, you said that in proofs, what we're doing is we're going from axioms, we're deducing something logical from that axioms, and we're ending up with the final result. How do we know that how do we know whether a deduction or a logical step is actually a valid deduction or a valid logical step?
No, okay, now you are getting into semantics of logic, so I don't want to get into this, okay. So you are getting into, that's what I'm saying, you are getting into the intricacies of language. You are trying to say what is this, so this is the first order, second order logic, deductions, how to form logical sentences, so this is, I don't want to get into this, this is the study of logic, there is a whole theory for that, okay. So that is a completely different direction. There is a whole theory for that, okay. So I don't know if Professor Arindama Singh has already talked to you. Did he do any logic? He must have done it, okay. So you must know it. So you know the answer to what you are asking. So it's the whole theory of formal logic and automata and things like that, okay. So I don't want. So the point is, I don't want to get into that, okay.
Sir, last question.
I want to get into geometry, okay. Yes.
Sir, last question, sir.
Yes.
We have this theory of logic. If we are using logic to develop this theory of logic, how do we know that the theory of logic is logical?
Yeah. So that's why I'm saying you should now go and ask Arindam this, okay. Arindam will be the right person to, probably what you should do is that you should go and read. Just search for on Wikipedia, search for Gödel incompleteness, Godel, Gödel incompleteness, okay. So that's the most, flabbergasting, mind-boggling thing about it, okay. So logic is not as simple as it sounds, all right. So you should read about that. But you see, this is getting away from what I'm trying to tell you. Yeah, if it is more about logic, let me not answer it, okay. Let me get into my geometry, okay, which is close to my heart, all right. Yes. Yeah, see, all logical questions, please, ask Arindam, okay, he is the right guy. But I want to keep to my trajectory, all right. So I want to tell you some interesting things. So let me tell you some interesting things. So here is another question. So let me get to the following situation. So you see, you take a triangle on the plane, okay. And then basically you draw these angles alpha, beta, gamma, the interior angles. Then alpha plus beta plus gamma is actually equal to pi, right? Where I measure the angle in radians, all right. Now, of course, you have a more general thing. Instead of taking a triangle like this, you can take a polygon, okay. So if you take a polygon with the n sides, let me call this as so this is so A1, A2, A3. So A1, A2, A3, so this is and then if you want this AN, so you see, so here I have alpha 1, this is alpha 2, this is alpha 3, and this is alpha n, okay. So then summation of all the alpha i's is what? N minus 2 pi, very good, okay. And you can prove this by just dividing the polygon into triangles, right? Okay. Now I'll ask you the following question. Now what you do is that instead of doing this, suppose I give you a triangle like this. Here is a triangle, and this is what is called a curvilinear triangle because the edges are curves, okay. So now again I have these, so I will call this as A1, A2 and A3, okay. And then I have these angles alpha 1, alpha 2 and alpha 3. Okay. My question is, if we calculate alpha 1 plus alpha 2 plus alpha 3, what is this? Okay. And more generally, I can give you a curvilinear, polygon. Oops. Okay. And here is A1, A2, A3, A4, A5, A5, A6. This is alpha 1, this is alpha 2. This is alpha 3, this is alpha 4, this is alpha 5, this is alpha 6. What is alpha 1 plus? Okay. How will you calculate this? And this is happening on a plane, okay. I can do the same thing on a sphere or a cylinder or a cone or an ellipsoid, okay, or some curved surface, okay. So for example, if I take in more generally I can take a surface like this, okay. On the surface I can draw some polygon like this, okay. And again I can mark the angles alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, and then ask you what is alpha 1 plus etc. up to alpha 5. Okay. So the answer is that there is a formula for this, you can do it. To get a formula for this is again for example, in the scope of differential geometry. Okay, and of course, I have to. So when I say this, I have to say a few things. The first thing is that there are two things that have to be clarified. When you say angle between these two curves, so mind you, this is a curve. This is a curve, that's another curve. So when you, what is this angle alpha 1? How do you define the angle? Because these are curves, they are not straight lines. So here is where calculus comes in. What you have to do is that angle between two intersecting curves is the angle between their tangents. That is the idea. So what you have to do is, how do I get this alpha 1? So here I am trying to tell you how calculus gets into the geometry of things. Okay, so the calculus gets into the geometry of things because things are curved. You see, that's the whole idea. Okay, whenever you are looking at things that are curved and you want to understand their geometry, calculus will come in. Both differential calculus and integral calculus will come in. Okay, so for example, here you will have, so you see, you will have this. So for this curve I will have a tangent, and for this curve I will have another tangent, and basically the angle alpha 1 is actually this angle. Okay, the angle between two curves at a point is actually the angle between the tangents. That's how it is defined. So for example, in this case, probably this can very well be 0 if these two curves are, if both tangents are like this. This angle is actually 0. Doesn't look like that. Okay, this is where calculus comes in. Okay, so the angle, so when you say angles of a curvilinear triangle or polygon, you are supposed to take the angle between the tangents. Okay, and if, I don't know how many of you have done calculus, but finding the tangent direction is the same as finding this slope of the tangent is exactly the derivative. So that's how differential calculus gets into the picture. Okay, and a limit is coming because tangent is actually a chord. You draw a chord. If you want tangent at a point, you take a nearby point, draw a chord, and then you draw this chord, and then this chord becomes the tangent in the limit when the nearby point approaches the given point. So there is a limiting, and when you do this limit, you get the slope of the the tangent as the derivative. Okay, you know that. That's why So therefore, the moral of the story is that measuring these angles already involves some calculus. I want you to understand. Okay, that's one thing. Then the second thing is that what is special about there's something special here. So I want to tell you some trying to give these formulas involves what is more generally called the Gauss-Bonnet theorem. This is one of the landmark theorems in classical differential geometry, okay, which involves curvature. But then I will try to tell you some interesting facts. Okay, so the first thing is what is the so there is this idea. What is so special about straight line segments in ordinary geometry? What is special about straight line segments?
Slope is constant.
Pardon me?
Slope is constant.
Slope is constant. Okay. What I mean in terms of distance, if I give you 2 points in the plane, what is the speciality of the straight line segment joining those 2 points?
It's the
shortest
shortest
distance.
line.
Okay, so it's the shortest distance. So actually, this triangle. Okay, the beauty with the straight line segments are that they are shortest distances. Okay, now these shortest distances, I can ask for the same question, shortest distances between 2 points on a surface. So if you give me a curved surface like this, I give you 1 point here and I give you another point here, then I can draw many curves on that surface from this to that. Okay, and the question is, which curve is going to give me the shortest distance? First of all, will there be a curve that will give me the shortest distance? And if there is such a curve, what is the value of that shortest distance? Okay, so again, this is a question of differential geometry. Differential geometry says that there is a curve with shortest distance. Okay, and you can also compute that distance. Okay, using calculus. Okay, and what are these curves with shortest distances called? They are given very special names. They are called geodesics. So there is this idea of geodesics. Geodesics are, you give me 2 points on a curved surface, you find a curve of shortest distance. For 2 points on the plane, the curve is just the line segment joining the 2 points, and that's so easy. Okay, that's just because the plane has 0 curvature. Okay, so it was very easy. okay. But there are curvatures where these curves can look very counterintuitive. So for example, if you take geodesics on the plane, then these are straight line segments. If you take them on the sphere, they will be what are called as great circles, arcs of great circles. So what is that? So basically, if you draw a sphere like this, okay, then if you give me 2 points on the let me say 2 points on the sphere, okay, then what you can do is, of course, you do the following thing: draw a circle passing through those 2 points, okay. But there are many circles that can pass through those points. How do you get a circle passing through those 2 points? You just take any plane passing through those points and cut the sphere by that plane, okay. So basically what you can do is you can do something like this. You can just take, I can cut this, I can cut by a let me see whether I can draw this. I cut by a plane like this, okay, okay, and when I cut by a plane like this, what happens is that I get a circle. So let me not put this. I'll get a circle like this, and I'll get a circle, okay, and then I get this I get this arc, okay. So this is one way of getting arcs, but this arc, when it will have shortest distance, it will have a shortest distance only when the plane passes through the center of the sphere, so that it's part of what is called a great circle. A great circle is exactly the one that cuts the sphere into 2 hemispheres. It's like an equator, right? An equatorial circle. So the point is that if this circle, if this plane through P and Q, and if I take center of the sphere is O, this is center, then this arc, this circle will become a great circle, and this arc will be the geodesic, okay. So on a sphere, the geodesics should be taken along equators, and by equator I mean give me any 2 points, find the unique section by a plane passing through those 2 points in the center of the sphere. You will get a big circle passing through those 2 points and take the smaller arc. That is the geodesic, okay. Now what is the analog of, so I am trying to tell you, give you what you are going to an answer for this formula, but in a very special case. See, here in the plane, the sum of the angles is pi, but notice the special thing is that the sides are all geodesics. They are all straight line segments, okay. And of course, if this edges are curved, you really don't know. Its formula is complicated because it's basically because of curvature, But if you want to have an analog of the triangle on the sphere, you get what is called a spherical triangle. What is a spherical triangle? It's a curvilinear triangle on the sphere, except that the edges are now not just any curves, they are geodesics. So they are arcs of great circles. So this is what is called a spherical triangle, okay. So what you can do is, you can take a sphere like this, and then you can draw a spherical triangle, and so basically what happens is that you have I put one arc like this, this arc of a big circle, and then I put another one like this, which is arc of another big circle, then I put one more which is let us say another arc of a big circle, okay. All the 3 are arcs of big circles, and then you take these angles alpha, beta and gamma, okay, and assume that the sphere is radius 1, okay. So then what happens? Alpha plus beta plus gamma is greater than 180 degrees, sum of the 3 angles of a triangle. So this is a spherical triangle. So sides are geodesics. These arcs of great circles, okay. Alpha plus beta plus gamma is going to be greater than 180. That's because because it's bulging out, the angles are going to be, if you add, it's going to be more, but by how much? Okay, you know the answer. Yes, what is the answer?
It's going to be 3 pi by 2 total.
No, not necessarily. It can be anything. It can be anything, but within a boundary. So the I know what you are thinking of. You are looking at a situation where this is like it's like a piece of orange, right? You are just cutting it by like this. So it's suppose this is I am at the center. You are cutting like this, and then you are going like this 90 degrees, and then you are going to go back. So I get all three 90s. So you said 3 pi by 2. That's what you are thinking of. If you are thinking of that, that's correct. Okay, but I need not really bend at exactly at this. So angles can change, but there's something interesting going on. So this is again very, very beautiful. See, sum of the three angles of a triangle, spherical triangle, is greater than 180. What is the difference? What is the defect? The defect is if you calculate alpha plus beta plus gamma minus pi, you'll be surprised. What is the difference? It's actually the area of the triangle. Okay. The curved surface area. So when I say area, I mean curved surface area. See, it's very interesting. The curved surface area of the triangle is exactly the defect. It is exactly the excess angle. Okay, and you can now guess, if you, instead of taking a spherical triangle, if I take a spherical polygon, I take a curvilinear polygon on the sphere, all the sides are all now going to be arcs of great circles, but it's a polygon. If you take the sum of interior angles of the curvilinear polygon, it's going to be greater than n minus 2 pi. And what is the defect? It is the area of the curvilinear polygon. Okay, so it's very interesting. The defect, the difference, the excess is actually measuring the area. Okay, and so this is one beautiful fact. Okay, so people who wanted to do a project, I wanted them to. So this is part of what is called as spherical trigonometry. Okay, and this was very much used in those days when advanced technology was not available for navigation in sea, for so many things. Okay, so I mean, even now, if suppose all satellites break down, radar communication systems break down, or if there is an enemy ship, then you have to go silent. You cannot emit anything, because if they know your position, they will bomb you. Okay, so you have to go silent. If you go silent, then you don't have any electronics. How do you navigate? So there's always one guy who is a navigation master. He'll have maps. He'll have a sextant. He will have local time. He will have global time. He will have an atomic clock. He will immediately tell you, we are here and we are moving in this direction. Okay, there's one guy who needs to know spherical trigonometry, who is sitting there. Okay, all right. So about a year ago, it was so important that spherical trigonometry was a standard subject. But now everything has been subsumed by satellites and GPS and everything like that, but still you need to know. Okay, so this spherical trigonometry is a very, very beautiful branch. Okay, and it's completely derived from differential geometry. Okay, so you had a question. Yes.
Has this been proved or just
No, it's everything that I am saying here as a statement is proved, and we can prove it. Okay, so I wanted people who want to do a project, I will ask them to do some. So one of the interesting things they can do is do spherical trigonometry. Okay, understand?
Sir,
it's doable.
I have a doubt.
Yes.
So let's say that you said that alpha plus beta plus gamma minus pi is the area. So if we double the if we double the size of the sphere, and obviously the area will also be doubled, right, sir? Okay, but it will change, right, sir? But we are considering only the angles alpha, beta, gamma, and pi, which is a constant. So how will the area remain the same even if we increase the size of the sphere?
No. That's why I said unit sphere. If it is a sphere whose radius is not 1, then the formula will involve the radius. It will involve the radius.
So how will it change? How will the formula change?
The formula will be the difference in the angle will be equal to the total Gaussian curvature. Okay, so it will get multiplied by. So essentially, it will get multiplied by r squared, where r is the radius of the sphere. So if you change the radius of the sphere to 2, then it will get multiplied by 4.
Got
okay?
it. Sir.
So it will get scaled. Okay, so this is with respect to unit sphere. Okay, so this is how the effect of curvature. This is all effect of curvature, and this is all part of Gauss-Bonnet formula. Okay, so that is one thing. But I want to say something very, very interesting. Okay, again something very interesting. See, in ordinary triangles, you can have two triangles which are similar but which are not congruent. Congruence is stronger than similarity, okay? But in spherical trigonometry it's not, okay? Two spherical triangles having the same angles are congruent. Similarity is the same as congruence in spherical geometry, okay? So that's another surprise, okay? That is also something that you can prove, okay? So similarity is equal to congruence in spherical trigonometry. Okay, similarity is the same as congruence. Congruence is of course similarity, because congruence is very strong, right? Congruence means, you can move this picture to the other one by a rigid motion and superimpose it, okay? That is what congruence is. Similarity is you can scale it, okay? In ordinary geometry, because curvature is 0, you can scale and keep it similar but not congruent. In spherical geometry you cannot do it, okay? Alright, so this is and the surprising thing is that one of the projects that I wanted people to do is that you do spherical trigonometry. In ordinary trigonometry, what do? You do sine rule, cosine rule, okay? Then you do Hero's formula, etc., blah blah blah. Try to do that for spherical triangles, okay? So you can do it. When you do it, you will be surprised to find that once you give me the three angles of a spherical triangle, I can get you the lengths of the sides. That's the formula. That means the three angles accurately give all the sides. The angles determine the sides. In ordinary geometry, the angles determine only the cosines and sines and ratios of those of the sides by the cosine rule or the sine rule, right? But in spherical trigonometry, the angles determine the sides. If I give you three angles, you can write out all the three side lengths, okay? So that's spherical trigonometry. So that's something that's beautiful, you can do it, okay? All that it requires is some good knowledge of cross product of vectors, right? And some matrices, so you should be able to do it. Yes, you have questions, yes.
Said that congruency and similarity are the same in spherical geometry. So let's say that in normal Euclidean geometry I have two shapes which are congruent. Let's say they need not be triangles or polygons or anything, they can be any shape, any curve. So they are congruent in Euclidean space. Now we change the space, we morph it, bend it, whatever you want. Will they still be congruent in any other space?
No, what do you mean by morph it? Morph it means you see if you change this, if you change the space, then it depends on how you are changing it. Are you changing in the space in such a way that so there's something called local isometry. Are you changing it in such a way that you are preserving local distances? If you are doing that, nothing is going to change.
Let's say we take the sheet and make it into a cylinder.
Then nothing will go wrong. It will be the same. That's what I said. See, the plane, which is 0 curvature, the cone, and then the cylinder, they are all locally isometric. So geometries will remain the same, even though curvatures are different. So everything will match. But however, it will not match with what is happening on a sphere. It will not match with what is happening on an ellipsoid, for example. Okay, it will not match. So it's a question of how you are changing the curvature. So you see, it's very clear, no? It's a question of how you are changing the curvatures. You see, when you roll a cylinder, what is happening is that there is along the vertical, along that line, the curvature is 0. You are only curving it in one direction. The other direction, you are making the curvature, you are keeping the curvature 0. That matters, because what is called as a Gaussian curvature is a product of curvatures. One of them is 0, so Gaussian curvature is still 0, just like the plane. Okay. Similarly, when you take a cone, what is happening? If you take a generator of the cone, that's a straight line. So these are all examples of what are called as ruled surfaces. On ruled surfaces, you have straight lines. On straight lines, the curvature is 0. And what happens is when one of the curvatures is 0, the Gaussian curvature is 0, it still behaves locally like a plane. It's isometric to a plane locally. So plane geometry will not be affected. The problem is when you change curvatures in two directions, like for example on a sphere or on a torus or on a more complicated objects. Okay, that's where things change. So it was Gauss who was smart enough to realize that you have to measure two directions of curvature and take the product of curvatures, which is square of the arithmetic, the square of the geometric mean. He was a smart guy to see that you have to take the geometric mean and the arithmetic mean. Arithmetic mean is just average. Geometric mean, I have to take product and take square root, but the square root doesn't make any big difference, forget the square root, so take square of the geometric mean. There is just product of the curvatures. And Gauss was smart to realize that these two measures can already do lot of amazing things, certainly. Okay, so that's not obvious, that's what I want you to understand. Okay. So these are all some magical things happening in spherical geometry. Okay, and then you have a question. Yes.
So the assumption we make when we say that similarity is equal to congruence is that we assume it's a unit sphere. So
yeah.
Similarly, even on a plane, similarity is going to be equal to congruence when the distance is the same, right?
No, I think so. The question is, do you understand what I mean by that? What I mean is similarity equal to congruence means, what I mean by that is if two figures are similar, okay, then they are actually congruent. Okay, so if you apply it to triangles, it means that if two triangles are similar, then they are actually congruent. That's not true in a plane, right? Because I can take a triangle and simply shrink, scale it to be small enough. I can take an equilateral triangle and make it a small equilateral triangle. They are still similar, but they are not congruent. You cannot superimpose one on the other. But you try to do it on the sphere, you can't do it.
So
you cannot you cannot help similarity without bringing in congruence. You cannot have a similarity which is not congruent.
Yes, sir. So my question is, can't we just scale the sphere?
No, even if you scale the sphere, it will not change. It's not going to do anything. So that's what I am saying. See, this is the magic the constant Gaussian curvature of the sphere is doing. Okay. No, that's why you see. That is why you do this kind of math, because you get to prove that. Okay.
Sir, will you provide the proof of the expression which you have given?
Pardon me?
Sir, can you provide the proof of that?
Oh Lord. Yeah, so at least in one of the projects I would like to, somebody can, I think there are some students who are assigned, they can look at it, and then at the end, they can talk to others, or there will be a presentation at the end. Hopefully at that point they will give you a proof of that. In fact, I think I will again ask if there are some slots. I would like to take another couple of hours and tell you about many interesting things. Okay, but yeah, proof involves some work. Okay, I don't know how much calculus you guys know. Have you done differential calculus, integral calculus?
Sir.
If you have done it, then it's kind of you can do it. But I will try to also give a non-calculus approach proof. You assume something and then start from that, and then you can derive everything. Okay.
Sir,
so
most of us will have glimpse of calculus, sir.
Pardon me?
Sir, like
you have had a glimpse of calculus.
Yes.
That's all right. See, the idea is that once you know the framework, you can write out. See, you guys are going to be here for about a month, right? If I'm not mistaken. So yeah, there's a lot of time. So you can do a little bit of calculus that is required. It's very basic calculus, and then you can understand that. Okay, it's not difficult at all. Okay, but the point is that you have to bring in calculus to do all this, because everything is curved. So you need to you have to use calculus. Okay, so this is something that was interesting that I wanted to tell you. There are still many more interesting things that I want to tell you about, but let me pick among them. I still seem to have about 10 minutes. It's like a spoil of riches. There are so many other things I want to talk about. Among these, I wrote down several. Just hold on for a moment. I wrote down several things here that I want to tell you. The Storus business. Okay. There's something that I can tell about. Okay. So, yeah. So let me tell you about some global theorems. So this is again, I am telling you basically certain things which can be proved with with minimum amount of calculus and with some intuition. So here is another. So here are some. So there are some interesting global theorems about curves. Okay. So So there's the first thing. So again, mathematics abounds with statements which are as I always say, statements which look so obvious, but whose proofs are very, very difficult, or sometimes there are no proofs at all. People believe they are true, they are conjectures. So here is one more statement like that. This is what is called as a Jordan curve theorem. Okay. So what is this Jordan curve theorem? See, the idea is very, very simple. You start at a point in the plane, okay, and then you start walking, okay, and you're supposed to walk continuously, and there are a couple of rules you have to follow. You should never cross your own path, okay, and then after a finite amount of time you should come back to the starting point. So you see, basically, you go like this, you go like this, and then you go wherever you want, and then finally you come back. Okay. So such a curve is called a Jordan curve. A Jordan curve is a continuous curve which starts at a point and ends at a point. So basically it's like in principle it's like a loop, but it's a loop, but it's not really a loop because it can go around. Okay. You start at a point, you come back to the point, and it can be, if you draw something, if you draw something very easy, this is a very, very easy way of something like this is also a Jordan curve, but it can be pretty complicated. See, for example, I can draw something like a maze. So it's harder to show this. I can draw something very, very like a maze, and then okay, that's also a Jordan curve. Now you see, so you can imagine that I can draw a very maze-like curve which is so twisted everywhere, horribly twisted curve, but which satisfies this. So what is the Jordan curve theorem? It says something very, very simple. It says that any such curve has an interior and an exterior, okay, which is obvious. Okay, if you take something like this is the interior and this is the exterior, right? Similarly, if you take this one, again it's obvious. Whenever I show you a picture, you will immediately say this is the interior, okay, and outside you have the exterior. But if I give you a very complicated curve which is like like one of these mazes that you solve, then if you zoom in, you cannot say what is inside and what is outside. Okay, all right. Now the fact that this is always true is called the Jordan curve theorem. It's not easy to prove. Okay, the easiest proof uses what is called as algebraic topology, which is a mixture of topology and algebra and mathematics. It's not an easy theorem to prove. Okay, but it's obviously believable. Okay, so this is, see, mathematicians always grapple with these things which look obvious, but for which you need a proof. Unless you give me a proof, I am not happy with it. So this is called the Jordan curve theorems. So these are all theorems on global curves. Okay, so this is one theorem. Okay, let's not worry about just about the proof, but I'll tell you the proof is not obvious. Okay, and the proof really becomes complicated if the curve is complicated. Okay, and the curve can become pretty complicated. Okay, how complicated can curves become? As mad as you want it to be. So Peano, a mathematician called Peano, discovered that there are what are called as space filling curves. There is a curve which you can map to a solid region in space and fill it, and this region need not even be 2-dimensional or 3-dimensional, it can be n dimensions. Okay, so this is, when he did this, people got scared again. There are things people do in mathematics, mathematicians do, and other guys really get scared. So what Peano did was, you can just take a continuous image of a line and then fill n-dimensional space. These are called space filling curves. So don't think curves are simple. Okay, they can run counterintuitive. Okay, so don't take curves lightly. Okay, that's, as a mathematician, that's what I will say. All right. So this is, so let me come to the next important. So this is a more interesting theorem. So there is something called isoperimetric inequality. So what is this isoperimetric inequality? See, it's again, so this is again an example of something that happens physically, for which you want a mathematical explanation. The mathematical explanation comes from differential geometry. Okay, so take a drop of water and put it in space, where there is no gravity, you know it will become spherical. Alright. Take a bubble, blow a bubble, it's always a sphere. Okay. Of course, I am assuming there is no wind or something like that. Okay. You take, take a loop of thread, okay, and then put it on a table, and then inside the loop you start pouring water, put a little bit of water until the water just wets the edges, and you will get a perfect circular shape. Okay. Why is this happening? Physics will tell you it's because of surface tension, right? Because of surface tension. That's all right. So you see, here is again something very deep. Lot of mathematics is already buried in physics. Okay. And what physics will tell you is what is surface tension trying to do? It's trying to, it is trying to minimize the, the surface. In a way, minimizing the surface is like maximizing the outer surface, if you want to say. Okay. Or you are trying to minimize the surface area. All right. And then the point is, when you say you are minimizing something, there is a mathematical thing. Okay. So you can translate from physics to math and say, is it true that when you are minimizing or maximizing something, there is only a particular shape which will do it. So for example, what is a mathematical statement? Suppose I give you a drop of liquid, that means the volume is constant. For constant volume, what is the shape that will minimize the surface area? Sphere. Okay. Similarly, if I give you a loop shape, okay, and you look at the area inside the loop, but I keep the perimeter of the loop, the circumference, if you want, okay, I keep that length fixed. Okay. Keeping that length fixed, I can get all kinds of amoeba like shapes, and I have the area in between. What will give me maximum area? Circle. So great, as physics guys and as people who are thinking, I say hail, but then I will say this, I won't accept it until now I become like Professor Calculus in Tintin's comics, prove it for me. Okay. Prove it means prove it mathematically. Among all curves, closed curves, okay, which are like loops of fixed length, show me the shape of a circle is what gives maximum area. Prove it. Yeah, I mean it will be minimum, but you have to, actually there is a curved surface there, and it's the curved part that you are trying to contract. I mean, at least look at it as a, I think the best thing that you should do is that if you take a soap bubble or something like that, okay, then the one that will give kind of uniform surface tension will be the spherical surface.
Yes, sir. So we need a minimum surface area and for a constant volume. And then in this case, why not minimum?
So minimum surface area for constant volume is the 3D version.
Yes,
2D version is you need maximum surface area for constant boundary perimeter. That is the 2D version. In the 2D version, the maximum is you get a maximum. Because you see, I can take a piece of thread and if I keep on stretching it, it will become like this, right? That area I can make it smaller and smaller and go to even 0. Literally when it's just a line segment going back and forth, there is literally 0 area. So there is no minimum. The point is only whether there is a maximum. And then the problem is that the maximum occurs only for the spherical thing. I mean, in the 2-dimensional case, it's a circle. So these are what are called as isoperimetric inequalities. They are called isoperimetric inequalities. Isoperimetric means the perimeter, the boundary measure is kept constant. So in the 3D case, the boundary is a surface, its surface area is constant. In the 2D case, the boundary is a curve, the length of the curve is constant. Okay. And for that constant, what is in the 2D case, what is the maximum area? In the 3D case, what is the minimum, maximum volume if you want. Okay. Then the shapes are sphere and for 3D and circle for 2D, and then you can do this in n dimensions also. Okay. Now, how do you prove this? So, as a mathematician, I will say, I am not ready to accept anything that you are going to tell me, give me a mathematical proof. And the answer to that is again differential geometry. Differential geometry allows you to prove it. That's because basically you are trying to say that the shape of the curve or the shape of the three-dimensional surface is a circle or a sphere, right? And that means basically these are shapes of constant curvature, right? So you have to show the curvature is constant. So it's a question of differential geometry, okay? So isoperimetric inequalities come from that, okay? So that's another interesting, fact. Yeah.
Sir, for the example that you gave, we kept volume constant and then we tried to minimize surface area of the object.
That is also true.
So the 2D analogous quantity of volume is area. Area
Correct.
in 2D is analogous to 3D volume.
Correct.
Perimeter in 2D is analogous to 3D surface area.
Correct.
So then why aren't we saying that keeping the area constant, which shape gives me the minimum perimeter? And why instead
Yeah,
why
you can
are
do
we
it
saying
both ways. See, if you keep the perimeter constant, then you can maximize area to get a circle. If you keep area constant, okay, then you can see that if you minimize the perimeter, then you will get the so either you maximize one and minimize the other. Either one of the two constraints you put, you will get the same effect. You will only get constant curvature. They are equivalent. In fact, why they are equivalent is again you can prove it using, that's again part of differential geometry. I mean that also can be proved. Okay, so it's all it's all math, and you can rigorously prove it. Okay, so that is one thing, and then so maybe one more interesting thing. How much time do we have?
What are isoperimetric inequalities exactly?
So isoperimetric inequality, if you want the statement, take a loop, take a curve like this, okay, length of gamma is perimeter of gamma, is L, which is constant, okay, and then this is the area of the interior of gamma. By the way, when I say area of interior of gamma, such an interior exists. Why does it exist? It's because of Jordan curve theorem. Okay, so you see that's why Jordan curve theorem is important. No matter how uglily this this shape may be. Okay, so you have the area of the interior of gamma. You see, this is maximum only for gamma equal to circle. Okay, that means what it means is that you see when gamma is a circle, that circle will have 2 pi r equal to L, right? Therefore, your so for that circle you will see that the area will be what? It will be pi r squared, and the area of this will always be less than or equal to this pi r squared. This pi r squared is what? Is pi into r squared is L by 2 pi the whole squared. This is pi L squared by 4 pi squared. So this is equal to pi, so L squared by 4 pi. So the statement is that area of the interior of gamma is less than or equal to L squared by 4 pi, and equality occurs if and only if gamma is a circle. This is the statement. Okay, this is called the isoperimetric inequality. You can get a lesser area, but the maximum you can get is a circle, and that happens only when the curve is a circle. Any other shape, it will become smaller. Area will become strictly smaller.
Sir, so is this inequality does this inequality hold only in Euclidean space, or does it hold in any other space?
No, this is Euclidean space. See, if you go to other geometries, things will strange things will start happening. So let me give you one more example. I think we are very much into tea time. So I will give you an example of geometry in which the shortest distance between 2 points is not the shortest distance that it looks like. Okay, so the standard example is you take the unit disk. Okay, circle centered at the origin, radius 1, and I am looking at this piece of the plane. So there's something. So this is something that is not directly obvious. On this, there is a negative curvature this is negatively curved. Okay. Okay. Now, what is interesting is that it doesn't look negatively curved to you and me, but actually you have to do a little bit of deeper mathematics like complex analysis, okay, or differential geometry connected with complex analysis to show that this is actually hyperbolic, namely this has a negative curvature. And I will tell you what that curvature is. So the best way of understanding a curvature is to understand geodesics. What are the segments of least thing. So here is a geodesic. So you take a point, take another point. What is a geodesic? The geodesic is always a circle passing through those 2 points with the property that the circle is orthogonal to the unit circle. This is the geodesic. So moral of the story is that if you call this arc length as S, and if you call the direct line segment L as L, then S is less than L. Okay. And when you say S is less than L, of course this is nonsense. It's nonsense if you are looking at it as Euclidean geometry. When I say S is less than L, this is with respect to what is called as hyperbolic metric. And the beautiful thing is that this hyperbolic metric has curvature -1. So it's negatively curved. See, it's because it is negatively curved, straight line distance is bigger than a curved line distance. Okay. And the only case where you will get straight lines here is if you take any line segment through the origin, any diameter will be a geodesic. That's because diameters are orthogonal to the circle. Any other, any 2 points of diameter, the line, the distance will be, that will be the shortest distance. But here is another surprise. In this geometry, if I take a point here, and if I take a point Q, let me put some R, which is very close to the boundary, and measure this distance. Okay. So here and at the boundary, let me take this point on the boundary as, let me say, as R0. Okay. What you can do is you can let R tend to R0 and measure this distance R. Limit. Guess what?
So which surface is that exactly? Is it a hyperbolic?
It is a model of a hyperboloid. It's a model of a hyperboloid. So this hyperbolic geometry, this is one of the models. Then there are 3-4 models. There is a Beltrami-Klein model. There is a Lobachevsky model. There is a Poincaré half disk model. There are many half plane models. There are many models. Okay. So this is a very strange kind of negative geometry that is already embedded in plain sight, but you can't see it unless you do, for example, conformal geometry or something like that. You cannot see it. So it was Lobachevsky. It was a great Lobachevsky, Russian geometer, who said that you can have negative curvature. You can make sense of negative curvature, because people realize that negative curvature is exactly the kind of situation that will have, so that straight line distance will be more than a curved distance. By going in a curve, you are actually reducing a distance, which is kind of completely counterintuitive. That can happen only if the curvature is negative. Okay. So people were, is there a negatively curved geometry? So Lobachevsky was a person who showed that it is really true. Okay. So I want to tell you one more surprising thing. So this R is the length of O. It is OR length in the hyperbolic length. Okay. If you take this as R tends to this, R0 is on the unit circle. You know what is this limit? Anybody wants to guess? No, I am just measuring from the center origin to a point on the unit disk, which is very close to the unit circle. So R is this point, and I am measuring this distance. Okay, I am measuring this distance. So let me put some other color. I am measuring this distance from here to here. Okay, I am measuring this distance, hyperbolic distance. All right, I am not ordinary Euclidean distance. Of course, if I measure ordinary Euclidean distance and take R to go to the point on the unit circle, I will get 1, because it's unit circle. All right, but I am not measuring unit. I am measuring hyperbolic distance. Now, as I measure hyperbolic distance and let R to tend to R0, what do you think will be the limit of the hyperbolic distance?
It will be a chord of the circle with diameter 1.
No, Baba, I am asking length. What value do you think it will be? Yeah? Anybody wants to guess? Okay, here is the answer. You won't believe it. This unit disk, okay, to your eye it's bounded. In the hyperbolic metric it's infinitely, it's unbounded. As you approach the boundary circle, you are at infinite distance from the origin. Okay, that's how it is curved. That's because the negative curvature. Okay, hard to believe. Okay, see, these are the tricks that curvature plays on you. That you have to understand that. Okay, why is this happening? That's the property of the hyperbolic metric. Okay, you have a finite object, you know, but distances are trying to go to the point on the boundary is impossible. You will never reach it. Okay, so that is the beauty of the hyperbolic metric. So I mean, these and many more things await when you do differential geometry. I will try to see if I can get a couple of more hours and tell you some more interesting things somewhere later on, where let's see if there are some slots. Okay, I think I should stop now, because there's another lecture and then you need to grab. I also want to grab a cup of tea. Okay, so let me stop. Anybody has any questions? Quick questions? I know people have lots of questions, but yeah, and usually I am very talkative and I am also very slow, so I wanted to say many more things. Hopefully I will get another couple of slots, and I will again, I will contact Arun and find another couple of slots, okay, to tell you some interesting things. Yes.
So is this figure a projection of the hyperbolic space, or is
it is actually a projection of the hyperbolic space? So that infinite, so you can imagine this infinite hyperboloid. I am making a projection. So you are going to the boundary of the hyperboloid, which are asymptotic, right?
So it's like we are looking down.
You are looking downward, exactly. You are just projecting downward. So what is happening is, as you go to the boundary, you are going deeper and deeper down into the hyperboloid. You are literally going to infinity, negative infinity. Z axis negative infinity. That's what's happening. Okay. But the point is that this is in plain sight available with you just do complex analysis, what is called as conformal geometry. With ordinary complex analysis, what you have to do is, what calculus you do, you take real functions, you take limits, you do differentiability, integrability, you do, right? You write f of x, where x is a real variable. Try to do that for f of z, where z is a complex variable. Take a function of z, where z is a complex variable, and try to do the same calculus. Then then this negative curvature will be revealed. Okay, that's how it comes up. So it comes up in a very theoretical way. All right. Yeah. So I think we will finish it for the moment. I'll try to find another slot where we can continue this. Okay. Yeah. So.